First, we are going to explain an excitatory circuit. On the right is cell number 1, which is our cell that produces glutamate. Glutamate is the primary excitatory neurotransmitter in the central nervous system. When glutamate is released into the synaptic cleft, it binds to ionotropic receptors, which are right here on the dendrites of the cell. In this example, the ionotropic receptor glutamate is binding to an AMPA receptor. This causes a conformational change in these voltage-gated sodium ion channels. Sodium rushes into the cell through these gates, which depolarizes the membrane, meaning the voltage begins to rise from its resting potential, which is negative 70 millivolts. This is going to lead to an excitatory postsynaptic potential, or an EPSP. In order to fire the action potential, the voltage needs to reach the threshold, which is negative 55 millivolts. Usually, multiple EPSPs are summated at the axon hillock to reach the threshold. So, once the threshold is reached, the action potential will fire. The sodium and potassium channels open. However, sodium ion channels open a lot faster than the potassium. So sodium is going to rush in, and as the cell's potential depolarizes to about 40 millivolts, the voltage-gated sodium channels will close, and then voltage-gated potassium channels open, and potassium will move out of the cell. This begins the repolarization process. The membrane potential drops below its resting potential after the falling phase. This stage is the relative refractory period, where the cell cannot fire any more action potentials. It is also called the undershoot phase. The sodium ions are going to move down the axon by diffusion, and this will regenerate action potentials at each node of RON-VA, where more voltage-gated sodium and potassium channels are located. Once that action potential reaches the axon terminal, the voltage-gated calcium channels open, which causes an influx of calcium into the cell. The calcium is going to bind to the snare proteins, and this is going to trigger the vesicles carrying the neurotransmitters to fuse with the cell membrane. And in our example, since this is an excitatory cell, the glutamate is released into the synapse out of the vesicles and binds to the receptors on cell number 3, which is the postsynaptic neuron, where this whole process happens all over again.
In our second example, we have an inhibitory circuit where cell number 1 is still excitatory, so it still releases the glutamate ions, and they still bind to the AMPA receptors, causing the voltage-gated sodium channels to open, and the action potential occurs, moves down. But the difference is when the calcium ions enter cell number 2 and bind to the vesicles, causing them to bind to the membrane, the neurotransmitter that is released is an inhibitory neurotransmitter known as GABA. And GABA binds to the ionotropic receptors. In this case, we're using GABA A, which results in the hyperpolarization of the cell membrane via a chloride ion influx. So the resting membrane potential decreases, and this results in an IPSP, or inhibitory postsynaptic potential, in which cell number 3 is much less likely to fire an action potential compared to the excitatory cell number 3.